All right, so we've talked about the basics of signals and systems. We've talked about the basics of analog communications. We've talked about how we can think about bits being transfigured to signals and then those signals being transmitted. And then at the other end, the big idea is that was completely different than an analog modulation. We have a finite set of choices to choose between in our receiver. Before it was design a receiver circuit that would tease out your sent message, which is a continuous function of time, and which could have been any continuous function of time. But actually, the digital receiver design problem, I think, at least conceptually, it's much easier. It's pick from a finite list of things, pick which one was most likely to have been sent. Okay. So what we're going to try to do now is fill in the gaps. We're basically taking that original big picture of a communication system and working our way inwards. And so this unit is talking about line coding, which is how bits get mapped to time domain signals. Okay. All right, so speaking of which, here's that big picture that I was referring to. So, and I guess it's not entirely true because we are going to talk about forward error correction. I think this is in module. What are we, 4, 5, 6? Call it module 7. So we're actually going to go back to there. But for now, we're going to focus in here. And then if we crack that black box open, we have this was our channel coding from the last slide. And inside of that channel coding, we are going to first talk about line coding. So taking bits and mapping them to these pulse shapes. And then, of course, we're going to actually get a little bit to this at the very end because it actually segues quite nicely into the next module, which is going to be OFDM. This guy, we're not going to talk a whole lot about this. So the fact that if you're multiplexing or not multiplexing, this doesn't really affect what we're going to talk about because it comes downstream. Okay, so questions about where we are in the grand scheme of a great big block diagram in the sky? All right. So the purpose of channel coding is that you want to get your symbols, equivalently bits, from transmit to receive as quickly as possible and with as few errors as possible. If you have few errors in transmission, then you have fewer errors for your error correction code to take care of, and everyone's happy. But at its face, that you immediately see that there's tension. If I want to do something quickly, I am going to be more error prone. The quicker I try to do it, the more errors I'm going to make. Like that's the fact of life that I'm sure you all have experienced in one form or another. It's true for digital communications as well. So what are our constraints? Any engineering problem needs a robust discussion of the constraints. Well, the channel you're trying to send your data through, it's going to have a finite bandwidth. And what that means for us is that we have a limit on the highest frequency oscillation that we can send through it. And that highest frequency oscillation actually has definite implications for the data rate. So this is actually a kind of a good sidebar into what's called Nyquist channel capacity. And so as a side note, we're going to later talk about Shannon channel capacity. And the difference is that in Shannon capacity, noise is taken into consideration. But in Nyquist, this is in the absence of noise. Okay. Shannon had to come along, 30 years later after Nyquist and say, well, I mean, yeah, what you said is true, but it's also not practical at all. Sorry, we'll get into historical beefs later. Okay, so if it bears the name Nyquist channel capacity, there has to be a factor of 2 in there somewhere, right? That's what we all know Nyquist for. So if your channel bandwidth is limited to B hertz, then Nyquist says sample at 2B samples per second. I'll just abbreviate that with hertz, and you get all the info, right? That's what he's famous for. But if you sample twice per cycle in the highest frequency cycling thing, then you can only contain in that highest frequency component 2 bits per cycle. If we're only sampling it twice, then at most we could have 1 bit in the first half period and 1 bit in the second half period. So this implies no more than 2 bits in the highest frequency component. Right? If you tried to put in 3 bits, but you were only sampling twice, you'd miss every third bit. And so this gives us a maximum data rate based on a bandwidth. So your data rate, RB, is no more than 2B bits per second. And this comes purely from Nyquist's sampling theorem. Okay. Data rate. So what the assumption that was, I guess, questions on that? It's pretty straightforward, but it does require you to think about connecting bits to sampling, which we haven't really stressed so far. If you also allow, because there's nothing to say if your bandwidth is fixed, there's nothing stopping you from amplifying the signal to multiple levels. And so we can actually modify this. So for what are called emery signals, this always bothered me. It should be Mary, right? But it's pronounced emery, M-ary, binary, ternary, quaternary. Anyway, emery for emery signaling. And what is that? That's just code for M bits per signal. Then your capacity actually grows to 2B or not to be. Just kidding. 2B times the base 2 log of your M level.
Capacity of bits allowed?
Capacity data rate. So this is the, so yeah, capacity in this context means maximum data rate. Right, view this from a digital communication standpoint, is the capacity of this channel is a gigabit per second. Okay, that means that any design that you implement cannot hope to get more than a gigabit per second across it, right? You could make compromises, you could get something under that, but it gives us a benchmark against which to measure performance of different designs. Again, in the absence of noise. You could also see this in like in the converse statement. So this is data rate is bounded by bandwidth, but if you flip that around, you can get for a given data rate, what is your required bandwidth, of course. So this would be, so this is one and the same with your bandwidth must be at least 1/2 times your sampling time or your bit time etc. So again, this tension about how you view things. Do you have a data rate that you need? Well, then you need to go and find a good channel, a wide bandwidth channel. Are you presented with a channel and said, do the best you can? Well, this would be the way to measure what is the best anyone could possibly do in terms of data rate. All right, this is going well. One bullet point down. I have a question. Those of you who are taking the lab 456, how much time have you spent talking about multipath effects?
None at all.
Okay. Jack says none as well. Fascinating. It was my impression that Professor Derrickson's one of his favorite things to talk about was multipath effects. He must be showing great restraint. Okay, that means that I get to introduce to you multipath effects. Yay. It is exactly what it sounds. If I have a transmit antenna and a receive antenna, and they are floating in deep space, then the direct, what we call line of sight path, will be the only path that a signal will take from transmit to receive. And that's because even like regardless of the, what do you call it? I'm revealing my RF lack of vocabulary here. Isomorphism? No. Isotropism. Regardless of how isotropic or not this antenna is, it's going to emit stuff in pretty much every direction. Different powers in different directions, sure. And the more directional your antenna is, the stronger the line of sight beam will be relative to the other beams. But if we're in deep space, then anything that's adjacent misses and never comes back. Okay. So all this is to say, if you're designing deep space antennas, multipath is not really a concern. If you're designing antennas for mobile phones or base stations or anywhere where there are multiple paths that a signal can take, for example, if these antennas are, on the ground, then the ground can reflect based on the frequency, based on what's going on, and not just that pair, but all of these. Yeah. And so at the receiver, so far we have been modeling. We transmit one thing, we receive one thing. Job done. But you RF people are kind of cringing, I think, when I say that, because of this multipath effect. And so the big idea is so there will be some time delay, right? So time delay, it'll be small because we're talking about speed of light here, but conceivable, especially with higher and higher frequencies that we are actually kind of coming into the realm of speed of light type speeds. But tell me, will the time delay, call it time delay 0, will the delay on this path be shorter or longer?
Should be longer.
Yeah, there is no path with less delay than the line of sight path. Does that make sense? So what you're going to get is kind of the baseline delay. And in fact, so far in this course, I've been just assuming the only time we actually considered this was in the radar ranging problem. But in truth, there's going to be delay introduced all over the place. But if you have a dominant line of sight, then it's usually good to model this pulse as just happening at time equals 0, the same time that this pulse happened. But what we're going to do is we're going to add to that pulse of t minus t delay 1, and then pulse of t minus t delay 2. And this will be attenuated. We've talked about that. Maybe this will be attenuated more because the reflection eats away some power. It's a slightly longer distance, so we get a 1 over r squared type path loss, et cetera, et cetera. And in the limit, right, this is endless because there are an endless number of multipaths that the signal can take. All this is to say is that if you start with a signal that lives nice and neatly between 0 and TB at your receiver, you are going to have some delay. We tend to get signals lasting longer in the receiver than they did in the transmitter. Okay, so how long this tail is and how important the tail is a measure of the multipath effect. And what it's called in the biz is inter-symbol interference. The idea being that you could be the only person on Mars, and if you're transmitting from one antenna to the next, you are going to interfere with yourself across time because of the paths bouncing off the dust particles or the ground or your rover or whatever, right? Let alone other people transmitting. So this is inter-symbol interference as opposed to interference from other transmitters. I think that a lot of RF people will say that there's no problem you have that more power can't solve. I'm putting a lot of words in the RF people's mouths, but they're not really speaking up for themselves, so I'm going to keep doing it. But in truth, you're limited in power, like in practical terms, either governmentally or cost-wise, or if you're doing this on Mars, you probably have a limited power budget because it's expensive to generate power. And then, of course, we've also talked a little bit about noise in the channel. So these are the four main constraints that we have when deciding how to turn bits into pulses, right? You can see that I've already started to make some assumptions here by drawing a pulse in this shape. Didn't have to be that shape. In fact, that's the whole point of this module is why that shape? Why not other shapes? Questions about this so far?
When you are adding an extra time, like the plus D0, is that stretching the pulse or is it just adding to the end of it?
So if you're not talking about Doppler, then it's just adding. So yeah, I tried to say that this distance is still TB wide. It just happens later in time. But if you start talking about Doppler, then all of a sudden, even signals that started TB seconds long, then themselves can grow or shrink depending on the relative speeds of the two antennas. I don't think I'm going to talk much about Doppler, but it's a common it's a common. Everything works if you don't consider Doppler. That's I think you're going to hear me saying that a lot.
So the area under the two curves is the same from 0 to TB, or?
So the area under the curves, probably, if this has normalized height 1, this will have normalized height no bigger than alpha, because we have to consider attenuation. That whatever the signal, the pulse starts as, it's only going to get smaller as we try to receive it further and further away. But like, if there were no multipath, then yes, everything would be scaled to live within D0 to TB plus D0, subject to 1 over R squared path loss. But I mean, it is true. And so we get into actually what I'm starting to think about next quarter. I think about 526, and one of the things that you can ask is, well, what if I had multiple antennas? Could I change what is viewed right now as a hindrance into an asset? Because what if instead of a single, so okay, we're getting a little bit off topic, but that's sometimes the favorite thing to do. What if you could plan on, if it bounces off the top of the slide, some of these going to one antenna and some other ones going to the other antenna? Could you do something intelligent about what was received on both of those antennas and improve your odds? So this is called, this is basically called a phased array or an antenna array, where the idea is that you line up antennas differentiated in space and try and capitalize on the non-uniformity of space to constructively interfere intelligently, I guess. So is that kind of what you're getting at, Sandra?
Yeah.
Yeah, just say yeah.
Thanks.
Okay. So let's talk about, this is enough time. Let's talk about the different possibilities for turning bits into voltage waveforms, if you like, or signals. So the most basic would be a 1-bit gets a positive pulse, and all these pulses are rectangles, but there's actually nothing, it's just because rectangles are easy to draw. So let's assume we're dealing with rectangles for now. And actually that's what the subsequent lectures will be talking about, is what can we do any better than rectangles? The simplest is simply 1 bits are on, 0 bits are off. Doesn't get any simpler than that. So I think you've seen this before. This is on-off keying. And this is in a returned to 0 sense. So what we've got here is the bit period, I think is consistent vertically. I borrowed this from the textbook. So if that's TB, then this is, say, tau less than TB. And the way it's drawn here, tau is 50% of TB, but you didn't have to do that, right? But a return to 0 simply means that tau is strictly less than TB, that in each bit period, the waveform returns to 0, regardless of what bit was sent. Let's see, the next guy is called polar, return to 0. So polar because it's a bipolar waveform. You're changing the polarity of the pulses here. Zeros become negative pulses, ones are positive pulses. And I misspoke about 20 seconds ago, because this is actually called a bipolar line code. All right, what's going on here? It's still positive pulses and negative pulses, but if you look, the thing that governs the positivity or negativity of the pulse is not the bit identity, it's the bit identity and the previous bit identity, or something like that. All right, so this is send a 1 as a pulse whose polarity is opposite of the last one's pulse. And if it's a 0, don't do anything. That seems like, so I mean, what would you have to do? You'd have to remember what you sent the last 1 as, and then do the opposite thing when the next 1 comes along. So it's harder to say in English than it would be to code, but it would require some memory, whereas the other ones don't require any memory. Okay, and then the bottom 2, this is again on-off keying, but in a non-return to 0 sense. And then this is polar non-return to 0. Okay, so I listed these as pros and cons, kind of assuming that we would just continue these rows across. But then when I was thinking about it, that, all right, when you assemble a pros and cons list, especially with like things that are exclusive, a pro in one row is a con in the next row, and you duplicate information. So I'm going to break with how I intended to present this slide and say, for polar signaling, what are the pros of polar signaling? You might be tempted to say that it requires, as a con, polar signaling. So let's compare these two. On-off keying versus polar, both of them being returned to 0. The average power in on-off keying is less, isn't it, for the same number of bits? If I don't do anything for half the time, then my power has to be less. So yeah, so you're right that polar in a con sense is requires more power. But I want to actually put this kind of in parentheses because we should not just measure this in absolute terms of power, but rather maybe power per bit error or bit error per power. Right, so what does it matter if you can send something with super low power if everything you send gets flipped? So I'd kind of go one beyond just thinking of minimizing power required and think about, you're not actually here to minimize power, you're here to get bits from A to B. And so we should actually be thinking of this in terms of which one requires the least power for the same error rate? Or for a given power, which one has a better error rate? And between polar and on-off keying, I don't think it's hard to see why polar has a better error rate per power ratio. So this actually has least transmit power per bit error rate. So even though it requires more power on average than on-off keying, if you then normalize by how many bits are flipped, this guy becomes, polar becomes superior to on-off keying. And I think the idea behind that is you can actually think of this in terms of constellations, where the constellation for on-off keying is positive or 0. And so the distance here is actually smaller than the distance if you were to do polar +1 -1. Bipolar is kind of the odd one out here. It has similar power efficiency in terms of error rate to polar, but it has one additional feature that is you can actually detect errors with this. This kind of has error detection baked in. So bipolar. This has a single error detection, not necessarily correction, included. Can you see why that would be? If you're sitting at the receiver, you're either going to get, say, a 1 or a 0 or a -1. If you get a bunch of zeros in a row, okay, could be right, could be wrong. If you get a 1 followed by the next non-zero thing was another 1, one of those ones has to be wrong. Okay, so you can't know which one was wrong, so you can't correct, but you can raise a flag and say, oh, excuse me, can you send that again? Retransmit request is what that's called. Okay. Yeah, so I mean that's kind of cool. But you have the similar kind of you don't have you have the downsides of on-off keying because that's essentially what you're doing. Because when we're talking about the magnitudes of these guys, you flip the negatives back to positives. And so this looks, in terms of a power consumption, like on-off keying. Okay, so let's talk about return to zero versus non-return to zero. And the essence here is if you do non-return to zero, you will be sending more energy per bit, right? Because your signal is on longer. If you're doing non-return to zero, so if you're kind of living down here, I think that you will have, in general, a smaller bandwidth. So let's think about these not in the time domain, but in the frequency domain. If I don't have to jump down every time the bit period expires, then I have these opportunity for runs, right? Lots of ones in a row means that I can leave my signal high for a long quote unquote time. And if I limit the variation in the time domain, then I will limit the width in the frequency domain. So this is non-return to zero has potential bandwidth savings with non-return to zero. Now those bandwidth savings are pretty much erased if you get 10, 10, 10, if you have lots of bit variation. So one could imagine that if this bandwidth savings was very important to you, that you could put something upstream of your channel coder that favored sending like bits together. Okay. But let me tell you why that's probably not a great idea. And that's because in the trade-off here, the pro for return to zero is you get timing reconfirmation, or timing, I'll just say timing data every bit. Every bit. Right? If you don't care what the identity of the bit is, and in every bit you jump down to zero, well then you get to know about the clock, you get to know about the phase every bit. Whereas here, I mean, the flip side of the bandwidth savings that I was talking about is if this goes on for long enough, this string of ones goes on for long enough, it's possible that your timing, your phase lock loop, can lose lock because it's not actually getting a reset every time. Okay, so if there's a small error, that error might grow over time, in which case you could lose your space in time. So that doesn't make any sense. You could lose your place in time. All right. There is another kind of non-obvious feature of the methods here that go positive and negative. So I want to point out that this guy and this guy, the on-off keying, are both going to have non-zero DC component because they never go negative. And that's usually unacceptable because if you have multiple links in your communication system, often the way that one link is linked to another is via AC coupling. And if you have information in your DC signal trying to pass that through an AC coupled interface, you're SOL. So this means no AC coupling allowed, which means, I mean, you could design your interfaces that they don't require AC coupling, but this has the effect of putting these signals kind of in their own corner of the playground, and no one can really play with them. Because if you use AC coupling anywhere in your network, say goodbye to on-off keying. Okay, so all of this taken together is, I mean, it's good to know because it lets you parse them out kind of piece by piece. But what has been adopted as standard, at least in Ethernet standards, is something called Manchester coding. And I didn't want to give it away, so bear with me while I draw it. In Manchester coding, basically trying to take the best of both worlds, best of return to zero and best of polar. And so the idea is, so let's see if I can. I'll just do a couple of them so you get the gist. In Manchester coding, each bit goes high and low. And depending if you're a 1 or a 0, you either go high first or you go low first. So in the original description of Manchester coding, a 1 bit went high and then low. So another 1 bit would go high and then low. And another bit would go high and then low. But then a 0 bit would go low and then high. Another 0 bit would go low and then high. Oops. If I don't give myself lines, low and then high. And then a 1 bit would be high and then low. So maybe if my drawing is not doing it for you, a 1 is high then low. A 0 is encoded low and then high, where low is negative, not 0, and high is positive, not 0. And I have no idea why, but it's the exact opposite in the IEEE 802.3 standard. So this is the OG Manchester code, but for reasons notes to them but unbeknownst to me, when the working group got together and drew up the standard called IEEE 802.3, which you and I call Ethernet, they said the opposite should be true. They said that a 1 should be low and then high, and a 0 should be high and then low. I'm sure they had, I'm not sure. They probably had a good reason for that, but I can't tell the difference. Okay, so can you see how this is pretty nice, because you get timing on every bit, regardless of it with 1 or 0. You get a DC bounce signal. It's going to be bandwidth intensive, right? So there are lots of chopping going on here. In fact, every bit requires chopping. So we're going to pay for this in the frequency domain. And that's kind of why this was for old Ethernet. New, like gigabit Ethernet, actually has a different line code. But I think it's nice to actually use a term that you associate with digital communications. I don't know. I thought that was a good connection to make, even though it's now outdated. Okay, that brings us to exactly 2 o'clock. That's perfect. Yeah, let's talk about what we should do instead of rectangles on Monday. I'll see you then.